Hi, welcome to a video. Today we are going to discuss about trees. So tree is a nonlinear data structure. So till now we discussed about the linear data structures. Linear data structures are the data structure in which the data are arranged in a sequential order, where nonlinear data structures are elements arranged in a non-sequential order or in a hierarchical data order. So a tree is a nonlinear hierarchical data structure that consists of nodes connected by edges. So these are the nodes 1, 2, 3, 4, 5, 6, 7, 8. These are the nodes, and all these nodes are connected with the help of edges. So this is a definition of trees. Okay. Why tree data structure? That is very important because we discussed about all the linear data structures like queue, stack, circular queue, double linked list, single linked list, circular double linked list, double-ended queue. So many linear data structures that we discussed. Then why we are going to study about the tree data structure? So other data structures such as array, linked list, stack and queue are linear data structures that store the data sequentially. That is why it is said to be a linear data structure. In order to perform any operation in linear data structure, the time complexity increases with the increase in the data size. Okay, that is very important. If you want to perform any of the operations like insertion or searching or counting or whatever it may be, if the data size increases, then the time complexity of that operation is also getting increased. Why? Because data arranged in a sequential order. We have to go to that particular order. We have to follow that particular order, either in the first in first out or in last in first out, or either from head to last node or last to head node, whatever it may be. There should be an order so that we have to travel accordingly. Then only we will reach to the destination. So that is the that is why we are saying that the time complexity increases with the increase in data size. Different data structures, tree data structures allow quicker and easier access to the data as it is a nonlinear data structure. So in nonlinear data structure, data are arranged in a scattered manner, not in a linear form, not in a sequential form. So whenever data is ready for insertion, then we will insert in the available location. So there is no sequential order, so we don't have any restriction that you have to travel in this particular order to reach this particular node. So we can choose the traversal order also. So that is the difference between linear and nonlinear data structure. That is why we are introducing tree data structure here. Tree terminologies, the important terms that we are going to discuss in the tree data structure are here. The first one is node. A node is an entity that contains a key or a value and pointers to the child node. Okay, here these are the nodes 1, 2, 3, 4, 5, 6, 7, 8. All these nodes represents data. So 1 is a data, 2 is a data, 3 is a data. Okay, here 1 is a node having one left child and a right child. 2 is having one left child and one middle, that is in the right child or second child we have. Likewise 5 is having 3 children, 6, 7 and 8. Likewise. So here the last node of each path are called leaf nodes or external nodes that do not contain a link or pointer to the child node. So the leaf nodes in these diagrams are 4 is a leaf node because 4 is having no child or children. 6, 7, 8 are a leaf node or external nodes. Okay, the node having at least a child node is called the internal node. So here 5 is the internal node, 2 is an internal node because 2, 5, 1 is a root, 2 and 5 are the internal nodes. So 2 having 2 children, 5 having 3 children, likewise. So all the nodes with children are said to be the internal nodes. Okay, tree terminology. Next tree terminology is edge. It's a link between any two nodes. Okay, here 1 to 2, 1 to 3 we have edges are there. So that is the meaning of the term edge. Okay, the next terminology is root. It is a topmost node of a tree. So 1 is the root node. So we will always travel from root to the leaf or root to a particular node. So root is the is like a head node. Okay, so we can start only from root node. The height of the node is the number of edges from the node to the deepest leaf. So for example, in this case, 1 is the root node, 2 is the internal node, 3, 4, 5 are the leaf nodes. Okay, so which one is the longest leaf from 1? So here 4 and 5 are the because we will count the number of edges in between from root node to the longest leaf. Here 3, 4, 5 are the leaf nodes, and 1 to 3 we are having only one edge. 1 to 4 we have two edges. 1 to 5 also having two edges. So here the height of the node root node is 2 because the longest or the largest number of edges from root node to the leaf node, that will be considered as the height of a node. For example, here too, if you are finding the height of 2, then what will be the height of the 2? 2 is having two leaf nodes, 4 and 5 both are having only one edges. So 1 is the height of a 2. Okay, we will discuss. Okay, the longest path from node to a leaf node is said to be the height of the node. Depth of the node is a number of edges from root to the node. The number of edges from root to the node is said to be the depth of a node. Here, for example, height of a tree. Here, the first node, we didn't mention any number for that node. So the first node or the root node, its height is 2 because the longest leaf, the number of edges to that longest leaf. So here it is 2. For in this case, 1 the height is 2, 2 the height is 1, 4 is having the height 0, 5 also having the height 0, and 3 is also having the height 0. Then depth of a node. The depth of the node is a number of edges from root to that particular node. Okay, so in this case, the root node having the depth 0, always the root node having the depth 0. And for example, in this case, for 2, the depth will be 1. Why? Because root 2, that the number of edges between root and that particular node is said to be the depth of the node. So in this case, depth is 1, and for leaf 3, depth is 1. For the leaf 4, depth is 2 because we are having two edges here. So depth of 4 is 2, and depth of 5 also 2. Okay, clear. Degree of a node. Degree of a node is the total number of branches of that node. In this case, 2 is having the degree 2. Okay, so that is the degree of the node. Okay, we will discuss the degree of the node in detail. Type of a tree. We have mainly 3 types of trees are available: binary tree, binary search tree, AVL tree, and B tree. So we are going to discuss about binary tree and binary search tree. So binary tree is a tree data structure in which each parent node can have at most 2 children. So we previous cases we discussed that tree is like no restrictions on that. Any number of child or children may be available in the case of a tree, but we restricted because if we don't have any restriction like any number of child or children is there for a node, then traversal will be very difficult because we don't have any. We should have some order or a rule to create a tree. Otherwise, traversal will be very difficult and searching time will be very high. So to avoid that, a binary tree concept is introduced. In this concept, each parent node can have at most 2 children. So 1 is a node having 2 children, 2 and 3. 2 is a node having 2 children, 4 and 5. Likewise, type of a binary tree. So full binary tree. A full binary tree is a special type of a tree, binary tree, in which every parent node or internal node has either 2 or no children. In this case 1, 2, 3, 4, 5, 6, 7. Okay. In this case 1, 4, 6 and 7 are the leaf node, 2 and 5 are internal node, 1 is a root node. So every parent or internal node, listen, this is a full binary tree. Every parent or internal node has either 2 or no children. Either 2 or no children. So that is a concept. In this case 2 and 5 are the internal nodes. So 2 can have maximum 2 or 0. 2 can be a leaf node or a maximum of 2 children. That is a condition for a full binary tree. Perfect binary tree. A perfect binary tree is a type of a binary tree in which every internal node has exactly 2 children, child nodes, and all the leaf node are at the same level. So in this case 1 is a root node, 2 and 3 are the siblings of siblings, and 4 and 5 also the siblings. Their parent is 2. 6 and 7 also the sibling, their parent is 3. Because here every internal node should have 2 children. That is the concept of a perfect binary tree. Next one is a complete binary tree. A complete binary tree is just like a full binary tree but has 2 major differences. Every level must be completely filled. Every level must be completely filled. So what is a level? So here 1 is a root node. So root node level is 1. Then 2, 3 are the next level. So okay. Root node is having the level is in the level 1. 2 and 3 is in the level 2. 4, 5, 6 are in the level 3. So the first one, every level must be completely filled. Every level. So 1 is the first level. 2 and 3 are the second level. 4, 5, 6 are the third level. So all the levels, that means you can't insert anywhere here. In this case of a complete binary tree, you have to fill in the order. First left, complete the insertion on the left child, then right, then left, then right, then left, right. So automatically all the empty spaces are filled in the order. So every level must be completely filled. All the leaf elements must lean towards the left. So in this case, this is the meaning of this last statement. All the leaf element must be lean towards the left. In this case 2 is completely filled because 2 is having 2 children, 4 and 5. 3 is not completely filled. It's also possible, but 3 is the internal node and having 1 left child. So the left part should be filled, then only we can fill the right part. So in this case the left part is filled with the element 6 and the right part is empty. So that is the meaning of that. All the leaf elements must be lean towards the left. All the leaf in the sense the leftmost elements should be filled first, then going to the rightmost element. If there is no element available to insert for the right element, then there is no problem, but all the leaf elements should be in the last level. So this is a skewed binary tree. So the skewed binary tree is either dominated by the left node or the right nodes. So here this is a left skew tree. This is a left skew tree and this is a right skew tree. All the elements are in the left part of every node. So one having one child, the node 1 having one child, that is 2, is available in the left part of that particular node. 2 is having one left child, that is available in the left part, that is 3. So this is a left skew tree, left skewed binary tree. And here this is a right skewed tree. 7 is a root node and having only one right child, and 8 is having only one right child. So all the right subtrees are filled. All the right subtrees are filled. That is said to be the skewed tree. Left skewed tree and right skewed trees are available. Then the balanced tree. Balanced tree is one of the type of a tree in which the height should be balanced. So here in binary tree, the searching time will be increased if the height of the tree is getting increased. That is very important. The searching time will be increased only when the height of the tree is increased. That is a very natural concept, because what we are going to do is, we will, if we want to search an element, what we will do is, we will go to the first element, that is a root element, then move to the left, then to the right, then to the left, then to the right. So if the height of the tree is increased, or if the height of the tree is more than 5 or 6, then the time consumption for searching a particular element will be high. So to avoid that, what we will do is, we will arrange the tree in a height balanced way. So how to balance the height? If a binary tree is a balanced tree, then the height of that particular left subtree minus right subtree, the height of the left subtree minus the right subtree should be either 0 or 1. So the height of the left subtree minus right subtree should be either 0 or 1. In this case, in this case, the height of left subtree is what? For example, in this case, for this particular node, the height of the left subtree is 1 and 2 minus height of the right subtree, that is 1. So 2 minus 1, 1. So it can be either 0 or 1. That is a condition. In this case, we have a left subtree and right subtree. The height of the left subtree is 1 and the right subtree is also 1. So 1 minus 1, 0. In this case, the height is 0. What's the meaning of that? It's a leaf node. So every node's balancing factor is said to be the balancing factor. So the balancing factor of every node should be either 0 or 1. That is said to be the balanced binary tree. I will explain it again. In this case, this is a binary tree and this is a root node, and this root node having one left subtree and a right subtree, and there are also two edges available. So the height of the left subtree is what? 2 minus the height of a right subtree, that is 1. 2 minus 1, 1. So the balanced factor that I didn't mention here. So the balanced factor of this particular node should be either 0 or 1. That is the condition for a balanced tree. Likewise, in this case, the height of a left subtree is 1 and the height of a right subtree is 1. So 1 minus 1, 0. Here this is a leaf node, so we don't want to consider this one for calculating the balancing factor. So the balancing factor of all the nodes or all the elements in a balanced binary tree should be either 0 or 1. Then the representation of a binary tree. Array representation of a binary tree. Here, convert a binary tree. First step is to convert a binary tree to a full binary tree. Here in this case, we have a binary tree here, and we are going to represent this binary tree in the form of an array. The first step is to convert a binary tree into a full binary tree. The second step, give the number to each node and store it into their respective location. So in this case, what's the rule of a full binary tree? What's the rule of a full binary tree? A full binary tree is a special type of a binary tree in which every parent node or an internal node has either 2 or 2 children. That you should remember here. In this case, we have we don't have that property. These trees don't have the property of a full binary tree. So this tree is like a node which is okay. In this case, the tree we have in this array representation of this tree, we have it's a binary tree because every node has a maximum of 2 children, a minimum of 0. So in this case, D is having 2 children, E and T. E is having left child and no right child, and Y is having no left child and one right child. Likewise, in this case, what we are going to do is, we are going to make this convert this one as a complete binary tree, full binary tree, like this. So we are convert the full binary tree into a full binary tree like this. We are just mentioning it like this. So
we are assuming that he is having one right child, and that also having, because all the leaf levels should be in the last, all the leaf should be in the last level. That is very important. All the leaf should be in the last level, then only it can be considered as a full binary tree. In this case, all the empty spaces are filled with dummy nodes. So this is for representing this one in the form of an array. It's an important concept, and the representation of the array may be asked for 2 or 3 marks in your university examination. So this is the way. What we are going to do is we are filled the empty spaces with the dummy nodes. After that, give the number to each nodes and store it into their respective location. So here we are numbering the nodes from root node to the leaf node. So root node having 1, left child having 2, right child having the number 3, then y with the number 4, 5 represents a dummy node, 6 represents k, then s represents 7. Likewise, we numbered accordingly. So while numbering, what we have to do is we have to first take the root, then to the left, then to the right, then to the left, then to the right. So likewise, okay. After that, what we are going to do is we are store those numbered values in the respective index. So d will be stored in the index 1 because we numbered d as 1. Then e will be stored in the number 2. So e is in the second location, so second index. Listen, 5, we don't have any element there, 5. So 5 will be kept as empty. Likewise, so 13 is an empty space, so 13 will be empty. And b is located in the 12th, so 12 will be filled with the element b. Likewise, so this is a representation of a binary tree. Hope you understand the concept. If you have any doubt, please contact me. Thank you.